Build a robotic chime machine that can play a song by itself. That's the task we were given for our freshman year engineering design course. But unlike most teams, my team wanted to encode the song data into the machine mechanically. Each note in the song would have a corresponding disc, called a cam, with cutouts carved into specific positions along its edge. As all 12 cams rotate together, each cutout lets the corresponding hammer drop, striking the chime and playing that note. But defining all those cutout positions manually would take dozens of hours. So naturally, I spent way more time developing a system to do it automatically. A system that starts with sheet music and ultimately produces 3D geometry that encodes the song data. But how? The animations you're about to see were created programmatically using handwritten Python code and Manim by Grant Sanderson. No generative AI was used. Music by Vincent Rubinetti and C418. First, I'll explain how the sheet music was exported as a MIDI file and read, then how the data was processed and transformed into a CSV file, and finally, how that CSV file was used to automatically generate the 3D geometry using Onshape's FeatureScript. I first opened the sheet music in my music notation software, then modified it to use only 12 unique notes and fall within the proper pitch range for our metal conduit chimes. I then exported it as a MIDI file, which stores data like which notes should be played and when, instead of the audio itself. But we can't just open this file and call it a day. We need a way to extract and process the data. That's where MIDI comes in. The Python library that can read MIDI files and spit out a list of messages. Each message is a MIDI object that has many attributes. For our purposes, we really only care about type, note, and time, which tell us the type of message, which note was played, and when that MIDI message was sent. The Python script first iterates through a list of all the messages in the song. Here are 6, for example. Now remember, each of these messages has an underlying type, note, and time, which looks something like this. The eventual goal for this Python script is to have a 2D list that will store note and time values for the song. So we'll create an empty list first and start filling it in. The first message is a note on command, meaning the note should start playing at the time of this message. So we put the note name in the left-hand column. But the time is a little trickier. The time values on these messages are relative to the previous ones, which we don't want. So we set up a time tracker variable to convert that to absolute time. The second message is a note off command, which we don't care about directly for this machine, but it has important time information, so we add it to the counter. For each note on message, the note value is added to the table, the time counter is incremented, and the new absolute time is placed in the table as well. For each note off message, the time counter is still incremented, but nothing gets added to the table. And the next 6 messages? By the way, the time value here is in MIDI ticks, not milliseconds. In this case, there are 480 MIDI ticks for every quarter note of the song. We could convert from MIDI ticks to seconds or beats if we wanted to, but there's no harm in leaving it for now. And there we go, a sequential list of each note that needs to be played and when. And these MIDI values are just representations of what would normally look something like this. Remember, our goal is to develop geometry for each individual cam. So instead of looking at all the notes in the order that they're played, we should be looking at all the times that each specific note is played. So we'll group by note value. The last step is to get this all into a format that our FeatureScript can read, a CSV file. We can form rows by listing every unique note that is played in the song. Then for each note, we can form columns that indicate every instance when that specific note should be played. For simplicity, we'll give each note a channel number from 0 to 11, each corresponding to one of our 12 cams. If we divide every time value in ticks by the length of the entire song, we can normalize each to be a value between 0 and 1. and then finally multiply by 360 degrees to scale it across the circular cams. So here are the rows corresponding to unique cams, and the columns specifying the angles where each note should be placed along them. We can now pack that all into a CSV file and send it to our FeatureScript. To fabricate the physical cams, we need to represent them as 3D geometry in CAD software, Onshape in this case. Under the hood, every modeling operation in Onshape, extrusions, fillets, patterns, is defined by code written in its custom language, FeatureScript. That means you can write your own features that generate geometry programmatically. So naturally, I spent 20 hours simply learning the FeatureScript language before I could even start building the custom feature. Here's how it works. The user uploads the CSV file from the Python script and sets other parameters in the feature's UI. And in a couple seconds, the custom feature generates all the cams. But the way the custom feature builds each cam is very different from how you or I would. Typically, when you use CAD, you have a graphical user interface to help you select things and snap points onto curves, for example. With FeatureScript, you need to write code to select the correct entities and often define point positions numerically. Behind the scenes, the script iterates through each row of that CSV file to build each cam. It uses a radial vector to specify the cylindrical body, and then defines the first cutout, which will be patterned later. We define the cutout shape in polar coordinates for design intent, a radius and angle for each point, and then use basic trigonometry to convert to Cartesian for the internals. Once the points are defined, it creates an arc with the top 3 points as inputs, a second arc with the bottom 3 points as inputs, and 2 straight lines connecting the outer points. That shape is then extruded into a solid body. The script looks at all of the angle values in that row and passes them into a circular pattern that creates an instance of that solid body at every angle. The initial reference cutout is deleted, and all of the other bodies are Boolean subtracted out of the main cylinder to create the cam's shape. The custom feature then sketches and extrudes a bore and key slot based on our specs, and writes the note number based on the index of that cam in the CSV file. As it iterates through the rest of the rows, it repeats the process and creates a unique cam for each one. And there we go. 12 automatically generated cams that, when rotated in unison at the right RPM, produce this music. Now, some might argue that all of this was a waste of time for a one-off use case. And they're probably right. But sometimes automation isn't about efficiency, it's just about having some fun. Thanks for watching.